Tonight I will be talking to you about cosmic train wrecks, what happens when two galaxies crash into one another. But what does it mean for two galaxies to crash into one another? Galaxies are fluffy objects. They're whole cities of stars, tens to hundreds of billions of stars. But it's not just stars. There's also gas and dust and dark matter holding it together. It's a very fluffy object, what we live in. So what does it really mean for something like this to crash into another such fluffy object? Can we really call that a collision? Now here I'm going to be showing you a simulation of just that. Two galaxies drawn together by gravity. But they're not going to crash directly head-on. They're going to pass each other by at least once and draw long strings of gas and stars from one another. But eventually, gravity will win out. And this time, they'll come back together in a much more head-on sort of collision. And when they do so, they'll really tear one another apart and send strings of stars, streams of stars and gas flying all over the place. These stars will eventually fall back onto the galaxy, and it'll be a new galaxy that will be born, not looking like its two parents, the new galaxy for our universe. So tonight, we will ask three questions. We'll start by asking, what really happens when two galaxies collide? What happens when the gas collides? What happens when the stars and the planets around them collide? And then I'll discuss how we study this process, both with observations and with simulations. And I'll finish up by discussing what this research can tell us about where the Milky Way came from and what will come in our future. So let's get started. So what happens when galaxies collide? Well, a galaxy collision is not unlike a courtship. You see someone across the room and you feel some sort of attraction. For galaxies, this attraction is gravity. So it pulls the two galaxies close to one another, but they seldom meet directly head-on, instead have one or more glancing passages. In the courtship analogy, this could be lingering glances across the room, or perhaps in olden times dropping a handkerchief as you went by. But eventually, the two galaxies will have a collision. And once that happens, they'll go through a period known as coalescence, where the material from the two galaxies can no longer be distinguished as coming from one galaxy or the other. And once that's done, the galaxy will slowly relax into a more normal galaxy shape. NGC 1316 is a nice example of this. If you look at the yellowish glow, that's light from the stars. It's fairly smoothly distributed. But if you look at this darker material, this patchy material, that's dust. It's still clumpy, it's still patchy, it's not smoothly distributed. So this galaxy is a nice example of one that's not fully relaxed, but it's most of the way there. So this dance is what happens to the galaxy as a whole. But a galaxy is made up of various parts. So what happens to various parts? What happens to the solar systems, to the stars in the galaxy? To answer that, we really need to answer how far apart are stars. So stars are typically a few light years apart. And as my slide says, this is not to scale. To illustrate the scale, I am going to need a volunteer. All right. So I have two stars here. They are the size of ping pong balls. I'm going to keep the sun, and I'm going to give you a star that fortunately is not as hot as an actual star. Now, can you take this star about the right distance from my sun to approximate correct scale? Take a guess, or ask the audience for help. The moon is a little far. Well, you're going to need to go a little bit further. If you could you take this star for me to Cincinnati? We'll wait. It's okay. Okay. Well, it's dark and rainy outside. It's okay. So you can imagine if I have a ping pong ball in Boston and a ping pong ball in Cincinnati, the likelihood that these two ping pong balls will hit one another is fairly small. So when two galaxies collide, what happens is that the star fields just pass right through one another, which is good news because we live around a star, and we would prefer not to collide with another star when we collide with another galaxy. And in fact, you may be asking yourself, well, do the solar systems collide? If this ping pong ball were our sun, the edge of the solar system would be roughly at the intersection of Concord and Huron Ave. So you can see that the solar system is not that large, and they too will not collide. Now you may be thinking, all right, so the distance between stars is quite large, and so they're not going to collide. But the distances between galaxies must be even larger, so how can you expect those to collide? And for this, I will need my second volunteer, someone quite strong.
Gentleman in the red hat.
Gentleman in the red hat. Come on. All right, what's your name?
Peter.
Great, Peter. Can you take this galaxy with 100 billion stars? It's not that heavy, I promise. All right. And I'm going to hold another galaxy, and we're going to simulate the distance between galaxies. So, if you could, can you take your galaxy to the other end of the aisle? All right. Now hold your galaxy up high. That is roughly the distance between galaxies on average. Now, Peter, come closer. Keep coming. Keep coming. Keep coming. All right, stop. Hold your galaxy up. Now we're talking about the distance between interacting galaxies. Now, who can imagine that these two plates could hit each other? Yeah. So, even though galaxies are far apart in strict distances, they're nearby with respect to their sizes. And that's why galaxies can collide, but stars cannot. Can we give a round of applause for our two great volunteers? Great. So that's what happens to the stars. Now what about the gas? Well, on the left here, I'm going to be showing you the same movie of the stars in a colliding galaxy, and then on the right, I'm showing you the gas. Understanding what the gas is doing is important because stars and the planets around them are formed out of the gas. The different colors in this movie of the gas give you an idea of the temperature. Yellow is cool gas, and blue is hot gas. So as the two galaxies come together, their gas will heat up because the gas, as opposed to the stars that are point-like particles, the gas is a fluid. Now, if you imagine pouring 2 glasses of water into a large bowl, you're not going to be able to avoid having the 2 streams of water actually colliding. So in a galaxy collision, it's really the gas that's doing the colliding. Now, I've shown you this movie of 2 galaxies in collision, and it's taken 30 seconds, maybe a minute. But how long does it actually take? And this is an important question for a graduate student, because if I want to observe a galaxy collision, and I'm observing a system like the antennae, could I have observed its progenitors at the beginning of my thesis? Unsurprisingly, the answer is no. But you may be wondering, is this the sort of system that Galileo could have observed 400 years ago? Or would I need to go to observations that the ancient Egyptians might have made a few thousand years ago? That's not quite long enough. I'd have to go a little earlier. I'd have to ask an Eoraptor from the early Triassic period to overcome his lack of opposable thumbs and his tiny brain to build me a telescope and figure out a way to conserve the data all the way until now. And you're never going to find a graduate student who's willing to wait a few 100 million years to graduate. I'm sorry, we're a little more impatient than that. So what can we do? Well, we can look for signs that a collision is in progress. And the first one that we can look for is called disturbed morphology. Now, morphology is an astronomer's way of saying shape. Galaxies come in 2 basic shapes, which are not unlike breakfast. There are elliptical galaxies, which are shaped like eggs or sometimes like cucumbers. And there are spiral galaxies, which are pancakes. And in this case, it's a nice apple pancake with the apples giving you the spiral arms. Now, this is the normal shape of galaxies. And when galaxies come together, they can disturb each other's shapes. So if I show you a small bit of the simulation that I've shown you up to now, you can see that as the two galaxies come together, they draw long strings of material from one another, and sometimes the material connects them, but they're clearly disturbing the nice even shape that the galaxies would have if there wasn't another galaxy nearby. Now we classified these different types of distortions in three basic classes. The first of them is tidal tails, which is nicely illustrated in this pair of galaxies called the mice. You can see that there's a tail here, and there's a tail curving around this way. And the way that tidal tails come about is given to you in their names. It's due to tides. Now on Earth, we have tides in the oceans, and they happen because both the Earth and the moon pull on the water. And as the moon goes around, it pulls the water away from the Earth and causes it to move around the Earth. In the case of galaxies, when one galaxy goes around the other, it'll pull on the stars on the external part of the galaxy. It'll pull on them so well that it'll pull on them to form these long streams of stars. Now sometimes this material can even connect the two galaxies. You can see that slightly here, but better here, and then we call that bridges. And then we lump everything else into a general category called irregular morphology. Now it's important to keep in mind that not all irregular morphology is necessarily a sign that a collision is happening. But if you've got both irregular morphology and a second galaxy nearby, then that's a pretty good sign that there's a collision in progress. Now what else can we look for? Well, we can look for enhanced star formation. Now if you recall, when two galaxies collide, their gases move around quite a bit, and their gases collide and compress. Now the movie that I'm going to show you here is a simulation from within our own Milky Way. We're going to have a supernova explode and send out a blast wave, which will cause gas to compress. It compresses in much the same way that gas does in a galaxy collision. When that happens, it encourages the formation of new young stars. So in a galaxy collision, the gas gets compressed and new stars are formed. Now, I'm telling you that new stars are formed, so let's take a step back and talk a little bit about the different types of stars. The two extremes of star types are blue O stars, which are quite hot, and cooler M stars, which are red and cooler. And then in the middle, you have whitish-yellow G-type stars, like the sun. Now here I'm showing them as all being the same size, but in reality, there's quite a difference. O stars are 18 to 20 times the size of the sun, and M stars are only about 3/4 the size of the sun. There's also a lot fewer O stars than there are M stars, but the O stars live for much shorter time periods. An O star starts with a lot more material, but it uses it up at a much, much faster rate. As a result, it only lives a few million years, maybe as much as 10 million years. In contrast, a star like the sun can live about 10 billion years, and M stars can live so long that we have not yet seen one die in the age of the universe. The short lifetime of an O star, however, means that it's very bright. It's using up its fuel at a much faster rate, and so it shines much brighter. So if we want to find young stars, evidence of young stars, we're going to be looking for O stars because they're short-lived. Now, stars don't form in any particular order. They don't form all the M stars and then all the G stars and then all the O stars. They form them as a mixed bag. So if we find O stars, then we know that stars of all types have been formed relatively recently. I introduced these stars by giving you their color. And that's important because for stars, the larger the star, the hotter the star. And star temperatures are directly related to color. You can also see that on Earth. Lava is at about 2,000 degrees Fahrenheit. And so it emits mostly in the infrared. But our eyes can't see infrared, so we see lava as glowing red. In an incandescent light bulb, the tungsten wire heats up to over 8,000 degrees Fahrenheit. It heats up so hot that it emits in the yellowish range. It's the same way for stars. Cooler stars like the M stars emit mostly in the near infrared. Stars like our sun emit a whitish yellow color. And then O stars are so hot that they emit mostly in the ultraviolet. Now again, we can't see ultraviolet, so these stars look blue to us. So if we want to find O stars, we need to look in the ultraviolet. But that's not quite enough, because galaxies, unfortunately, have dust. Now we like dust, because dust is useful in creating stars, and it's particularly useful in creating planets, particularly planets like the Earth that are made of heavier elements. But dust is cold, so any ultraviolet that is in the area gets absorbed by the dust. The dust then re-emits heat in the form of infrared. So if we want to get a complete census of stars that are both unobscured as well as stars that are obscured, we need to look both in the ultraviolet and in the infrared. A nice example of this is this galaxy called Centaurus A. On the left, you have the ultraviolet image, and you can see that there's this dark band across the middle. In the infrared, this band is really, really bright. It's a band of dust that's absorbing ultraviolet from stars behind it from our perspective, and then the dust is re-emitting in the infrared. So a third sign that we can look for is an active central black hole. At this point, we believe that pretty much any galaxy of any substantial size has a central supermassive black hole. And when we say supermassive, we're not kidding around. We're talking about black holes that are 1 million to 1 billion times the mass of the sun. The image I'm showing you here is an artist's impression of such a black hole. Now recall that as two galaxies merge, their gas is moving around quite a bit. As a result, a lot of it gets funneled to the centers of galaxies and ends up forming these disks around the black hole. And these disks are essentially feeding the black hole. But black holes, it turns out, are like toddlers. They're very messy eaters. They like to throw food to the floor and throw food to the ceiling so that you can never really get that stain out. And for black holes, this manifests in jets. Now here we have two images of jets in nearby galaxies. This is M87. It has a jet that's been observed by Hubble, but more frequently the jets are observed in the X-ray or in the radio, which is shown jointly in this picture of Centaurus A, which is the galaxy that I just showed you, and you can see that there's this dust lane as before. So these jets are quite large. You can see this jet in comparison to the dust lane that I showed you before. These jets can reach to the edge of the galaxies, if not further. So black holes are very angry toddlers who are messy eaters. So far, I've talked to you about the three major signs of a collision that happens, and I've shown you some simulations of merging galaxies that have shown you two large spirals coming in. And one thing you may be asking yourself is, are these signs the same for all collisions? Are all collisions very similar? What you're really asking is, are all collisions equal? And the answer, unsurprisingly, is no. If you have two large spiral galaxies or a little dwarf galaxy coming in to collide with a spiral, you'll get a different process. So first of all, you'll get a much more disturbed morphology in the case of the equal-sized merger. If you imagine two spiral galaxies coming in, the likelihood that they'll come in just so that they don't disturb each other and leave a disk is incredibly, incredibly unlikely. You're much more likely to come in at some angle, be it ever small, so that when you come in, you really disturb each other's disks and send material all over the place. And when you allow the material to settle back down, you'll settle back down into an elliptical galaxy. In contrast, in these more minor collisions, the little galaxy will come in on one side and will annoy the big galaxy on this side, and then come in and annoy the big galaxy on that side. But eventually the big galaxy will say enough and absorbs the small galaxy. And then it'll settle back down into a nice spiral. The other main difference is that you get much more star formation in the case of a major collision. Not only do you get more disturbance of the gas, but you start with two large reservoirs of gas that can form new stars. In contrast, in the minor collision, you're only bringing in a little bit of extra gas. Now, it should not be that much of a surprise to know that we're headed for one of these major collisions with the Andromeda galaxy. But I would be surprised if most of you knew that we're currently engaged in one of these minor collisions. There's actually a little dwarf galaxy on the overside of the Milky Way, so you can't actually see it in the night sky, who's in the process of being absorbed by our very own galaxy. So now that we've talked about what happens in a collision, let me move on to how we study this process and start by talking about observations. So let me first talk a little bit about the importance of getting a long enough observation. So this is an observation of the galaxy NGC 474, which is this blob in the center, this elliptical galaxy. How many of you can see concentric rings around this galaxy? The red arrows kind of give you a hint. So in this observation, in this image, I would say it's more of a situation of if you really, really want to see them, you might be able to see them. But if you observe the system for longer, this is what you see. Now, how many of you can see concentric rings around the galaxy? Exactly. So if you had just observed the image on the left, you might say, oh, it's a fairly boring galaxy, let me move on. But if you got the image on the right, you'd be really excited and go, well, there's clearly something interesting happening. Let me figure out what it is. So let me talk a little bit about the various telescopes that we use to observe colliding galaxies. Now, I talked quite a bit about using star formation as a sign of a collision in progress, and about the importance of looking both in the ultraviolet and in the infrared. One of the best telescopes to look in the ultraviolet is the Galaxy Evolution Explorer, or GALEX, which is a NASA telescope, a space telescope, looking in the ultraviolet, who ended its observations in September. And in yellow, I'm showing the near ultraviolet emission, and in blue, the far ultraviolet emission of two systems. On the left, we have M51, which is known as the Pinwheel Galaxy, and on the right, we have NGC 3430 up here, and NGC 3424 down here. Now let's compare what this image looks like to one taken in the near infrared with the Spitzer Space Telescope. So one thing that you may immediately notice is that M51 has a companion here. It does not have one in the ultraviolet. What does this tell us? Well, it tells us that the companion galaxy has to have a lot of dust. It has so much dust that it's absorbed nearly all of the ultraviolet, and that's why it's so bright in the infrared. In contrast, if you compare NGC 3430's ultraviolet emission to the infrared emission, it's actually larger in the ultraviolet emission. That means it's got a region on the edge of the galaxy with very little dust to absorb any of the UV. Now, Spitzer is a great telescope for observing warm dust. It looks from about 3 microns to 160 microns. If we want to get an idea of the cooler dust that's still heated by the ultraviolet, one of the best telescopes is the Herschel telescope, which is operated by the European Space Agency. So it gives you a picture of the cooler dust. So with these 3 images, we can get a complete picture of the unobscured star formation in the ultraviolet and the obscured star formation in the mid-infrared and far infrared. So you might say, great, so now we can compare a system that's early on in its collision and one that's later on in its collision. But would that really be a fair comparison? Not really, because M51 might just have more gas to make stars. So really, what we need to compare is the amount of star formation that's happening per mass. And to do that, we need to look in one more band, in the near infrared. We do that using observations from the 2-micron all-sky survey taken on the Paratel telescope. Now think back to when I told you about the different types of stars. There were the massive blue O stars and then the tiny red M stars. And there was a lot more of the M stars than there were of the O stars. There's several orders of magnitude more of these tiny stars. There's so many more of them that they make up nearly all the mass of a galaxy. So if we look in the near infrared, where their emission peaks, where they dominate the light of a galaxy, we can get an idea of the stellar mass in a galaxy. And so together, these sets of observations will allow us to compare the star formation happening in a galaxy to one happening in another pair of galaxies earlier or later on in the collision process. Now you might be thinking, well, you've got great images, but how are you going to get numbers like star formation rate or stellar mass out of images? Well, it's fairly easy to measure the amount of light that you get from each of these images. And from that, you can make a plot like this. So we're plotting the luminosity, and we're going from about 100 million suns worth of light to 1 trillion suns worth of light. So it's a lot of light, but these are galaxies. And so we're plotting the points in the ultraviolet, the points in the near infrared taken with 2 mass, the Spitzer mid-infrared points, and finally the Herschel far infrared points. And then we can fit this with a line that takes into account the amount of star formation that's happening and the amount of mass in the system. Now, if we were to purely do this, we might say, all right, so I need enough young stars to make this much ultraviolet. That's not taking into account any obscured young stars. And so what we'd really want to do is figure out what the galaxy would look like if there was no dust. And that's what the blue line is plotting. To figure out how to get the blue line, we say, all right, so we absorb enough energy to go from the black line to the blue line, and the amount of energy that we absorb in the UV and the optical is the amount of energy that we emit to get all of the infrared observations. This is why it's crucial to get both ultraviolet and infrared, because without infrared, we would have very little in terms of clues to figure out how to get from the blue line, from the black line to the blue line. Now, ideally, we'd be able to do this for galaxies at different stages along the collision. But it takes a few 100 million years, recall. This is very much like what would happen if an alien species who only lived 10 minutes came to Earth and wanted to understand an entire human lifespan. They couldn't watch one human grow up from a child into a human, into an adult, and finally into grandparents sort of age. So what they'd have to do is take snapshots, take a picture of a toddler, take a picture of a child, take a picture of a middle-aged person, and finally an old person, and line them up in order. And that's really what my thesis has been doing, is collecting this atlas of galaxies at different points along the collision and looking at how star formation changes across this sequence. So that's how we do it with observations. Now, simulations are great because you don't have the whole time problem. You can make 100 million years happen in about a minute, or shorter if you're pressed for time. So early simulations were much more difficult than what we can do nowadays. They had to do all of these calculations by hand. And so it would take many weeks to figure out how to get from this type of system, where you've got 2 initial galaxies coming in, and one of them has 60, maybe 70 stars around it. And you calculate each of these steps to figure out how the stars move as the 2 massive galaxies move around. But Toomre and Toomre, even in 1972, were able to figure out that from these sorts of processes, you could get tidal tails. They were even able to do that for specific systems. So this is the picture of the mice that I showed you earlier. And note how they were able to recreate this straight tail and this curved tail really quite well. They were also hampered slightly by the fact that, for the most part, nearly all of the observations were in the optical. So you could get a pretty good idea of what the stars were doing. But you had nearly no information about how the gas was happening, or what the ultraviolet emission from the O stars was doing, or what the infrared emission was. There was some observations, but it's not nearly the wealth of data that we have today. And all of these observations that we have today, we can put in to make much more complicated simulations with more than 60 stars. Now we can have millions of stars to make these great simulations. Now, our witch's brew is a little bit more complicated than before. We still have the basic ingredient of gravity. Gravity tells you how 2 galaxies come together. Gravity tells you how star particles stay attached to a particular galaxy or move from one galaxy to the other. But now we can also put into it physics about what the gas is doing, how the gas is colliding, how the gas heats up when you compress it, how the gas cools down as you allow it to expand. And this is particularly important because it's related to how stars are forming. Now, O stars, which are the short-lived stars, when they die, they like to do so in an explosive manner. They explode in supernovae. And the supernovae, if they're placed near the edge of the galaxy, can blow gas completely out of the system. And so the supernovae link back to what the gas is doing, and together the stars and the gas make up a lot of the material that the gravity works on. So it's an entire cycle that feeds back upon itself, and the physics become quite complicated. But we can make these great simulations now. But how can we compare them to observations to figure out if what we're putting in is giving us reasonable results? Well, in a simulation, you could place yourself within the galaxy and say, all right, so I've got 5 O stars in this direction and 6 O stars there, and I've got 10 M stars in this third direction. But you're never going to be able to do that with a real galaxy. We're never going to leave the Milky Way, or if so, it'll be far beyond my lifetime. But even if we were to be able to leave the Milky Way, we're never going to be able to travel to other galaxies, to stop at various points and get different counts of stars. What we need to do is figure out how the light from stars in galaxies passes through any dust and gas between us and these stars, all the way out to the external portion of the galaxy, where we've got our telescopes to get the light from these galaxies. So one thing that we can do once we understand how to make images of these simulated galaxies is to compare the shapes that we see in the simulations to actual galaxies. And that's what this movie is showing you. When you have the grayish-brown galaxies, that's the simulation. Then every so often, it'll fade out into an actual Hubble image of a pair of interacting galaxies. That was UGC 9618. Now as we move forward, we'll get an actual collision between the two galaxies. And with the benefit of simulations, we can rotate around to see what it would look like from a different angle. That's ARP 148. As the galaxies separate again a little bit, they're pulling out tidal tails, showing you a galaxy like ESO 7714. And sometimes the tidal tail arrangements can look different from different angles. So it's important to get an idea of what these different angles can look like so that you can have a better sense of where in the collision sequence a particular pair of galaxies might be. And finally, we have ESO 148-2. Isn't it neat what we can do with today's technology? All right. So now that we've talked about what happens when two galaxies collide and how we study this process with both observations and simulations, you may be wondering, well, why should I care? These galaxies are very far away. Well, these types of collisions is how the Milky Way came to be as we know it. And there are some occurring right now with the Milky Way. As I told you, this dwarf galaxy is in the process of being absorbed by the Milky Way. And there's a large collision in our future. So let's talk a little bit about the Milky Way system specifically. So how did the Milky Way grow into the galaxy that we know and love? So this is the Iris simulation of the formation of the Milky Way. So in the center, you've got the proto-Milky Way. And you can see that there's other proto-galaxies, these things that look like clumps of gas, that come in and collide with our Milky Way. When they do, they'll spend some time disrupting the Milky Way or being absorbed. And eventually, the Milky Way accretes enough material to grow into the galaxy that we know. And it also has nice periods where it's not being attacked by other galaxies. And in those periods, it likes to settle down into the nice spiral pattern that we know. One thing that's particularly nice about this simulation is that it's also been able to recreate the bar in the center. Our galaxy has been known to have this bar, but it's always been something that's been tricky to replicate in simulations. And so this new ERIS simulation is a nice example of where our galaxy may have come from. Now, this process of cannibalism isn't unique to our galaxy. Our sister galaxy, Andromeda, goes through a very similar process. It's about the same size as we are, so it probably had a similar number of collisions to get all that sort of matter. And we know that it had to have had a collision relatively recently, at least in astronomical terms. How do we know this? Well, unlike the Milky Way, which just has the single central supermassive black hole, Andromeda is a little greedy, and it currently has two. Now, these two central black holes will eventually merge into a single supermassive black hole, but at the present, we've found a clear detection of two individual black holes at its center. Now, Andromeda is the only other large galaxy in the local group. And it's decided that it's not quite satisfied with eating dwarf galaxies. It's a little bit hungrier, and so it's coming for us. It's coming for us at 120 kilometers per second. Now, those are units that astronomers like. I'm not sure that most of you really have an idea of how fast your car goes in kilometers per second, so let me give it to you in slightly more everyday units. The Andromeda galaxy is approaching us at 270,000 miles per hour. So it must be quite hungry to come that fast. So when is it really going to collide with us? I mean, is this something that you can use as an excuse not to do your homework, as an excuse not to pay your taxes? No, unfortunately, you'll have to do both of those. You've got a little time. You've got 3 to 5 billion years. But what will happen to the sun and to the Earth and to the solar system as a whole when we have this collision with the Andromeda galaxy? This is a question that two of our scientists here, Avi Loeb and TJ Cox, looked at a few years ago. And they did a number of simulations to figure out what might be happening to the sun as this happens. Now, they determined that there was about a 12% chance that we would get ejected into a tidal tail. So we'd be sent out in one of these streams of stars, which might be interesting. But there's a higher chance that we'll just move outwards from the center of the galaxy. Now, currently, so this is an artist's rendition of the Milky Way, we're about 2/3 of the disk of the Milky Way away from the center. It would probably be a wise move on our part to move away from the central black hole. Because recall, in a collision, gas gets funneled to that central black hole and it becomes active. And not only does it send jets away, but the disk of material that comes in gets really hot, and so it emits quite a bit of radiation. So the further away we are, I think the better for us. There's also a 3% chance we'll decide we're just too cool for the Milky Way. And when Andromeda comes in for that first glancing passage, we might just skip away and go join Andromeda for a while. Now, eventually, our two galaxies will merge. And so let me end by showing you a little bit about what that might look like. So we live in a universe full of galaxies. In an ocean of 100 billion galaxies. All of the dots that you see here are individual galaxies, individual islands, hundreds of billions of stars. Many of them are being separated by the expansion of space. But some of them will be drawn together by the attraction of gravity. Our sister galaxy, Andromeda, is the only large galaxy in our local group. Just like us, it was built up of collisions, some of them recent, and it's coming towards us at about, 270,000 miles per hour. If there are still humans on the planet Earth, in 3 to 5 billion years, this might be the view that you have outside of your bedroom window. It would be to see not but two crossing in the night sky in a sight that no human has seen so far. Our two galaxies will engage in this cosmic dance, coming together once, twice, before finally crashing together. And in this process, they'll draw long streams of stars into these glorious tidal tails. But they'll be destroying one another. They'll be disrupting the glorious spiral patterns of the galaxies. Eventually, gravity will draw these two galaxies together, and they'll have their own cosmic train wreck. When that happens, it'll be very messy, it'll be very disruptive, but galaxy collisions aren't so much about the destruction of the two parent galaxies. It's about the creation of a new galaxy. It's about new life. It's about the new stars that are born in these collisions. And around these new stars, you get new planets, and some of them may have new life. These new lives, hopefully, will have some astronomers that will observe this new galaxy that they live in and begin their own